All right. So let us begin. Okay. So to remind us where we were last time, right? So we started discussing the notion, right, of independence. Okay. And basically, right, independence is probably familiar with a lot of students, right? And the familiar version is this one, right? The so-called, multiplication version. But as we mentioned, right, is for intuitive purposes, right, it's better to understand it from the conditional version. And this actually has implication later on, or in more advanced courses when you look at things like conditional expectation and conditional variance. Okay, then independence will more often take this version, right, than that version. But anyway, right, the point about independence, right now is that you should kind of remember that um, it sometimes, or yeah, sometimes it doesn't come, right? Or at least you should check in a problem to see if, right, the independence that you want to use is given in a problem or not, right? If it's not given, then either you show it, right, or you check that it's not true, whatever, right? But you cannot like basically assume independence, you know, without kind of like checking, okay? Um, because independence, so I guess, right, has many sort of subtle uh, points. One of which, right, is the idea that you could have events that are pairwise independent, but not mutually independent, for example, right? So again, this is just reinforcing, right, the idea that, well, we should not take independence lightly, right? And then um, we moved on, right, to the idea of, right, basically the multiplication principle, all right, for calculating probability. So basically the idea is, right, to calculate the probability of the joint, you can condition, right, use a conditional probability and then multiply with what you conditioned on. Basically, right, that's it. So this, right, looks suspiciously, right, this looks suspiciously similar to the structure of PE times PF, right? But this is not, right? Of course, the reason is because you're using PE to an F here rather than PE. Okay. And this could cause a lot of confusion, or, you probably, or you might get the right answer with the wrong reason, that kind of thing, right? Because, for example, right, in the hat problem, right, 1 over n times 1 over n minus 1 is the right probability for both men getting the right hat. But, right, 1 over n minus 1 is not the probability the second man gets his right hat. That would be also 1 over n, right? But it's rather the probability the second man gets his right hat conditioned, right, on the fact that the first man already got his right hat, right, for example. So, right, so here, right, they're not independent. So there are other examples, for example, right, the urn problem when you sample without replacement, or, right, even the problem where you sample with replacement, right? So here, you might have, right, again, the sort of the intuitive idea that balls drawn, right, consecutively from an urn with replacement would be independent. But then again, right, look closely and the independence, right, is at least not given, right? It's not given, okay? Explicitly in the problem, right? You just say you draw on the ball from the urn without replacement, right? Sorry, with replacement, okay? So equally likely actually is more of like the natural assumption here, right? Each balls are equally likely to be picked rather than independent. And when you look at a structure, right, of let's say the joint event like this, right? picking like the blue balls, right? So the probability of picking two blue balls, right, is the probability of picking the first blue ball and picking the second blue ball given that the first ball is blue. And right, so this structure is always correct. And it comes out to be 4/9 for this one anyway. The reason, right, is because once you sample a ball, you put it back into the urn. So whatever you sample, right, has no effect on the probability of the second urn, right? So you're effectively saying this is PE2. And this is exactly, right, where you establish the independence between these two. But, right, once again, right, it's not given explicitly in the problem, right? Okay. And then, right, generally we have, right, we can do it for more than one event. We can do it for n events, right? We just have to kind of get it correctly. And the correct version, right, is that you need to condition, let's say, the last event on all the previous ones, and then the next to last on all previous ones, and so on, right? You cannot, right, do the short version like this, even though it's very appealing, because it won't get to anything, right? It won't give you any answer. I mean, of course, under some assumption that, the process, right, you're looking at is Markov, then you can do that. But, right, I mean, well, that would take us, right, to a different topic in a different course. In general, right, we're not dealing with Markov process here. So, for example, right, let's see how the cancellation goes. And then you'll see immediately, right, how the cancellation should not happen for this. So here we just give the example, right, for 4 events. So if you just use definition, right, this is E1, E2, E3, E4, right, over E1, E2, E3. And then, right, the next one would be E1, E2, E3, right, over E1, E2, right? And you see immediately that these two cancel. And, right, the next one is E1, E2, right, over PE1, right, times PE1, right? And again, right, you see the cancellation keeps happening, right, which gives you, of course, that. And then, right, you can clearly see, right, that this cancellation structure, right, this telescoping won't happen if you only use, like, not use the whole hell. You don't use the whole history, right? But you cut off at the most recent one. Is that okay? That's why, like, this multiplication won't get you to anything unless you have the assumption that somehow is equal to this one to begin with. Okay, any question about this? All right, so I think let's finish, right, the problem set 4 by going back, right, and pick up the problems that would use the multiplication rule. Okay, for example, this one, right? So this one, let's take a look, right? It's really not about conditioning, but it's about applying, right, multiplication rule. Right, that's all there is to it. Multiplication principle, right? So the point is we don't want to do this by counting. Now that we have the multiplication principle, right? Let's do it that way, okay? So let's give it like a couple minutes. I'll be right back. Okay. All right. Any suggestion for the solution of this one? The sound coming in okay, right? I'm not losing any sound.
Yeah, that sounds fine.
Okay, appreciate it. Thank you. So, right, you have the event as Y1, Y2, right? And then B3, B4, right? So that's what you want. Right? So what would that be? That would be something like, right, by the multiplication principle, sorry, it's long, right? Something like B4 given Y1, Y2, B3 times B3 given Y1, Y2, P of Y2 given Y1, P of Y1, right? Again, you don't, well, okay, it's better to write like this. So you see, right, that basically the sequence, right, even though we write like this, the time sequence, right, is we pick the first white, then we want the second white given the first is white, third black given that, so on, right? And so what is that? So first white, of course, is 6/15, right? And then second white given the first is white is 5/14, right? And then third black, which is 9, right, given the first two, and then second, fourth black. Is that okay? So that's by the multiplication principle. Right. Any question about this? Okay. So now the multiplication principle, right, can be applied to all the problems that we've done before. For example, I mean, of course, right, it depends on the problem. Sometimes some problems are not as, let's say, amenable, right, to the multiplication principle as others. But let's say this one, right, the spade card, right? So remember, we did this by counting, right, to get to this. And of course, right, this structure cannot change. This is the, right, I mean, how to say this? This is the, right, I mean, the conditional probability definition. But to get to the, right, the joint like this, you could use the multiplication principle if you like, right? For example, what's P S2, S3, right? We did this by counting, right? But what this would be is something like P of, right, S3 given S2, right, times P S2, let's say. Okay. So now you think about it, right? What's P of S2? What's the probability the second card has a spade? Well, if you just look at the second card and think that it is a spade, that's 13/52, right? And then condition on, right, that the second card is a spade, the probability the third card is a spade would be 12/51, right? Agree? Now, similarly, P of S1, S2, S3, you can do something like that too, right? And here, actually, sequence doesn't matter, but something like S3 given S1, S2, P of S2 given S1, P of S1, right? And so again, P of S1 will be 13/52, and then 12/51, and then, right, 11/50, right? And if we cancel, we get 11/50, right? Like that. Okay, so this problem, probably, right, if we try the multiplication principle, is easier to deal with than the counting. As long as you do it correctly, right? That's okay. All right, any question? Okay, so let's look at this, right? again, this one may or may not have anything to do with like the multiplication principle, okay? Just a problem right there. But okay. So we have three cards, right? Which we call A, B, and C, which have three values, right? And whichever they are, you can think of them as 1, 2, and 3, whatever, right? And permute, right? So given, right, A less than B, find the probability that A is also less than C, right? Like that. So, right, so this is P A less than C, A less than B, over P, right, A less than B, right? All right, so what do you think? Which one do we want to do first? Or let's say, right, what is the size of the sample space here?
This is just 3 factorial.
Okay, yeah, counting is always safe. All right, so which one do we want to do first? Let's try, I don't know, A less than B. Oh, you know what? Actually, this, as you'll see, will be easier. Right? What would this be? How many ways can A be less than C and A less than B?
Two ways,
Good.
C less than B or say greater than B.
Excellent, right? Exactly. Because if this is like that, then the value for A is fixed, right? A must be the minimum, right? So there's no choice for A. A is the minimum. Then the only choice is between B and C values, right? Which is two choice, right? Or two factorial, if you will. Is that okay? Then what about A less than B? How many ways?
Three ways, the two ways above include, and also that C is less than A.
Yeah, not bad. So, right, A less than B, which, right, of course, count these two ways, which is good. And so what else, right? So I guess, so what you're thinking of, good, that's actually a very good way to look at it. So A less than B, A less than C, right? Plus P of A less than B, C bigger than A, right? Because, I mean, right, this is exactly the, as you see, this is exactly the what we call the law of total probability, right? The next slide, but right. So we break it right into two scenarios, right? Technically speaking, something like equality, right, could happen, but because these cards are the values are distinct, right? Then right, we don't have that. And the beauty of this, or the suggestion is very good because we already know what the top is, right? 2 over 3 factorial. So we only have to look at this. But notice, right, this is a very specific sequence, right? A less than B, and then so C is less than A, so C less than A less than B, right? Oh wait, C, oh no, sorry, C is greater than A. Hold on. Let me try to see if that's true. 2 over 3 factorial, that's good. How many ways can this happen? So A is less than B.
I
And
think you
C
have to
is
write
great.
C less than A for that second term.
You're right. I think she said it correctly, right? And I just I just read it wrong. Yeah, okay, thank you. So yeah, that's only one way, right? Because this is the way. Yeah. No, I made a mistake. Thank you. Very good. So right, so the final answer will be right, 2 over 3 factorial divided by 3 over 3 factorial, right? Which simplifies to 2/3, but whatever, right? All right, good, very good. Any question? All right. Okay, let's look at this. Now, so 7, right? It only has a cute part for C. But notice that now we start slowly introducing, right, the independent assumption, right, into the problem. And why? Why do we introduce it here and not in the previous problems? Because the coin is biased, right? Remember that independence at the heart of it, right, is a quick way to describe the sample space, the probability on the sample space, right? When you have other ways like equally likely events, then you do not need to invoke independence as an extra description. And in fact, the two descriptions might be contradictory, meaning that, right, the assumption, independence assumption, right, is flawed, right? But here we can and we need to, because the coin is biased. Okay. So well, let me do the difficult problems for you. P to the 4th, 1 minus P times P cubed, right? Any question about this A and B part? All right. So let's focus on the interesting question, the C, right? What would C be? Okay. So notice, right, these kind of questions, like a pattern come before another pattern in general, right, would be, let's say, a difficult question, okay, would be a difficult question. And in the order of things, probably will belong in like a stochastic process class rather than this one. The reason why this one is here only is because it has a very easy way to look at it, right? This pattern has something in it that makes the question, even though phrased in this kind of scary way, you know, basically reduced to a simple observation, right?
I
And
can,
yeah,
oh,
go ahead. Go ahead.
I'm just gonna kind of like jump the gun on my answer just intuitively. I think it might just be P if I just kind of ignore like the last three outcomes of the coin flip and just look at the first outcome, the heads or the tail.
No, okay, let's go there, but let's kind of flesh it out, right? So okay, the first toss can be tail or head, right? And then what happens then? So this is the first toss, right? So what happens? Why would that be? Why would this be related to the pattern?
Well, here there's a P probability that it turns heads. So I don't know, maybe it just simplifies to just the probability being P. I kind of just guess though. I'm not really too sure.
No, right? That's not clear enough, and I think it's not convincing enough either, right? So because again, right, why would this correspond to the pattern, right? Had or whatever comes before, right? The other, for example. So right, the hint is there, right? How can the pattern had occurs first?
I think it's the only way it can occur first is if it's just it's what like it's the first four outcomes like in the problem A.
Right, that right. So I think so. So basically, right, this analysis, even though on the first toss, right, sounds reasonable, it doesn't lead anywhere, right? But so if we look at the first four tosses, right, either right, had come first, right? First four, right? In which case, clearly it comes before, right? Correct? Well, if not, right? If not, if first four is not had, that means that, right, there must be a tail somewhere, right? In the pattern, let's say, right? Something like this. Correct? Then why would this, what would this mean? So either, right, first four all heads, or there's some tail, right? A tail in somewhere, right? But then what? What's the analysis after that? The
Wait a
analysis
minute.
after
Is it
that,
just
yeah,
oh
go ahead.
um
Go ahead.
okay. So I was looking at it wrong before, but would it just be P to the fourth then? Because if P to the fourth didn't happen, being all four heads, then there would be a tails somewhere in the first four.
Okay, yeah. And then what?
Well, no. Oh, I don't know. I would just say P to the fourth is the probability that
No, notice you have not addressed the logic yet, right? You're saying, so you're saying that the probability that this pattern occurs before this pattern is the same as the probability the first four is all heads. Okay, that's
yes.
your claim, but why? Why is that?
Okay.
You haven't provided that explanation.
Okay, I see. So uh well, I guess I'm having trouble like formulating it exactly, but the
Mm-hmm.
probability of four heads occurring back to back is P to the fourth. So I don't, it's like the difference in probability. Like if P to
That's
the fourth didn't happen, then there would
so.
be a
First of all, right?
tails.
Don't confuse the number with the event. The number is P to the fourth, which is the probability the first four is heads, are all
Yeah.
heads. That's correct. The event we're interested in here are several. The event that this comes before that, and also the event that the first four is all heads, and the event that, right, the numbers don't come in here at all, right? So the logic is, or if you want to convince people, you have to explain why if there's a first tail, there's a tail in the first four tosses, then head cannot come before tail head, right?
Yeah.
So, all right, any other suggestion?
Uh, I think it's just because tail head requires only three heads and um like so if once you have a tail in there um like you only need three heads to form the tail head and so it will always
Correct.
happen before that, yeah.
That's good. That's exactly it, right? So either all the heads comes first, or the four heads comes first, or once you have the tail in there somewhere, right? Then exactly, because it's tail, head, to have four heads like this, you must have three heads first, but you already have a tail in there, right? So however you slice it, you will have tail, head before head, because you already have a tail in there. Does that make sense? A tail in there would prevent you to ever achieve four heads in a run before you have tail, head. Does that make sense? Right. So exactly that. Basically, the answer here is P to the fourth. But right, the argument is exactly because right, if you don't achieve this on the first four runs, introducing a tail in there, right, means that you will always have the three heads in a run before four heads in a run with that tail, right? Meaning that you will have tail, head before or head. Does that make sense? Any question about this?
Sorry, can you maybe just hearing it again will help me, but can you formulate the exact reason it's P to the fourth again?
Yeah. So again, right, so basically the idea is the event head, right? This pattern, right? This pattern comes before this pattern, right? Notice again, right? This is a pattern that can come anywhere in the sequence, right? We claim that this is the same as the event first four toss are all heads, right? That's our logic. Okay. So this is about event. Once these two events are the same, then that means the probabilities are the same, right? Okay, now the logic is why, right? The why actually is like this, right? Basically, right, of course, if first four tosses are all heads, then right, this, so basically, right, to show that E is equivalent to F, you show F implies E and E implies F, right? Or, rather, right, not F implies not E. Okay.
Yeah.
So clearly, right, first four tosses are all heads implies this is before that. Okay. Now, of course, the crux is about this. What if not all four tosses are heads, right? If not all four tosses are heads, that means there's a tail, right, in the first four tosses, right? Or, right, if you will, right, basically, so yeah, basically, right, you already have a tail in the first four tosses. But once, right, you have a tail like this, actually just run it through, right? Just run this through for the next few tosses to see what happens. Okay, what do you want? You want a head here? If you have a head here and you already finished the tail, head, right? So to prevent that, you must have a tail. But if you have a tail, well, the story starts again, right? You already have a tail. Then doesn't matter how much you go after that, right? The most you can go is three heads before you complete the sequence. You cannot have a sequence of four heads before you have tail, head, because you already have a tail in there. Does that make sense? So basically, right, just continue this sequence, for example, once you have a tail, right, anywhere. How would you continue this sequence? You either continue the sequence with a tail, which means you can restart the tail, or you can see you continue with a head. That means you finish the sequence. So you have tail, head before. Does that make sense?
Yeah. Okay. Thank you.
Yeah. Again, right, it's kind of cute, not that hard, but right, it's sort of not easy either, right? You have to recognize the equivalence of these events like that, right? Okay. All right. This is the last question for this problem set. Okay. So let's start with the last part, right? Which is really not a question, but right. I mean, it is a question, but it's not really the main point of the problem, right? But in the line of thing we're discussing, right? To solve this question, to be able to solve this question clearly, right? We want to make an assumption. And the assumption here, of course, is Barbara, right, and Diane are independent, right, in terms of their action, right? Okay. So, well, I mean, like, can we do that here? Yeah. So the way this problem is structured, it's kind of like want you to recognize, right? You have to make this assumption. Eventually, right, a question like this will have that kind of assumption built in, right, that is stated. And again, right, why is that the case? Like, why do we need that assumption? Because, right, the probabilities are something like P1 and P2, right? It's not something like, oh, Barbara and Diane are equally likely, right, to hit the target or something like that, right? So with the P1, P2, we cannot, right, build the joint probability, right, which is what we're being asked here about the joint action of Barbara and Diane, right, without making the assumption that they're independent. All right. If the problem doesn't give us anything but their joint action, the best assumption we can make is they're independent. Does that make sense? So, right. And by the way, also the second one is, right, notice, right, another thing we need to pay attention to is this word right here, right, if. So this is a conditional probability, all right? It's a conditional probability question without stating it out loud as such. Is that okay? Because of the word if. So part A is something like probability that both hit, given, right, that duck was hit or whatever, right? Okay, so how would we proceed here? Something like that, right? But what would the answer be? So clearly, right, if both hit, that implies the duck is hit, right? So duck is hit, it actually just at least one person hits is okay. So the first one clearly is P1, P2, right? What about the denominator?
P1 plus P2.
Not correct.
P1
P1
plus
plus
P2 minus P1 P2.
excellent. Don't forget inclusion, exclusion, right? The probability either Barbara hit or Diane hit is, right, the probability that it's the sum subtracting the joint, right? This is P of B union D is PB plus PD minus PBD, correct? So yeah, right, don't forget that part. All right. So B, right, is also, right, conditional question, right? The probability that Barbara hit, given duck was hit, right? Of course, it's going to be P of Barbara hits, duck hit, over P dot hit, right? And I guess this one will just be P1 over P1 plus P2 minus P1, P2. Is that okay? Any question? All right. So let us continue with the lecture. So the next thing we want to talk about, right, is the law of total probability, which is super important. This is a tool that sort of analyzes a lot of rules moving forward. Also, is a technique that allows you to calculate probabilities easily in some cases, okay, as you'll see. So this one is super important. I mean, the multiplication principle is also important, but it's more like, okay, yeah, right, use it correctly, it will help you simplify a problem. Otherwise, I guess you can do counting for now, whatever, right? But the law of probability is really a point of view that if you miss it, you won't be able to solve the problem. Okay, right, so what is it? So basically, right, we start out with a so-called partition of the sample space, right? Basically, just a bunch of events that have nothing in common, and the union, right, is the sample space. So in terms of the, right, picture is something like this, right? So you have E1, E2, E3, E4, E5, something like that, right? They all, right, occupy a part, nothing in common, and then they join up to be the whole sample space, right? And then you have some other event F that you want to calculate a probability of, right? So F is something like the red circle here. Then, right, clearly to calculate PF, you can just look at the part of F, right, in each of the component and then add it up, right? So this is clear. And in fact, right, we did use that in the, right, in the count right here, right, which is an excellent way to do it. Right, this one right here, that was exactly, right, an example of that, right? Again, except that technically speaking, we should do less than equal to, right? But there's no equality, so we just go to that. Now, but then, right, we can make it better by kind of use the multiplication principle on each of this, right? So this is the joint, we can break it down to conditioning times that. All right, the special case is when n equals to 2, then, right, we have E1 and E2 are just E and E complement, and then it's like that, right? And so why is this helpful, right? Isn't it just easy to calculate PF directly? Well, the answer is no, right? In the cases we've shown you so far, yes, right? Maybe you don't have a need to look at it like this. And by the way, right, what is this? Even though it looks like kind of symbolically scary, this at Harvard is just to divide into cases. That's what it is. So to look at the event F, you look at F if this happened or that happens, right? A natural thing, for example, is let's say the probability that you will bring an umbrella, right, with you. Well, maybe that is not easy to calculate, but then you can break it down to if it rains, what's the probability you bring your umbrella with you? And if it doesn't rain, what's the probability you bring the umbrella with you, right? Those are two natural cases to split the calculation under. The only thing, right, is that once you split that condition, then you have to pay back by multiplying with the probability, right? So in the example that we just cited, right, then you have to multiply with the probability that it rains or it doesn't rain, right? Like that. But it's a very, very natural thing to do, and it allows, right, when you break things into cases, actually things simplify rather than more complex, right? Of course, depends on the problem. Okay. Any question about this? All right. So to demonstrate, right now, let's go back to the one all the way at the beginning, right? The Monty Hall, right? Where we said, right, that we will give a rigorous explanation, right? Once we discuss the law of total probability. Okay, so again, right, the idea is, right, that you have three doors, right? One of them, behind them is a price, right? A car, the other doors empty or something you don't want, like a goat, right? You pick a door at random. Let's say you pick this one, right? And then the host would, among the other two doors, right, will show you a door that is incorrect, right? Let's say show you this one, right? The point is, right, it doesn't matter what door you pick, right? Because there are two doors that have the goat behind, right? The host kit will always be able to show you, right, the door with the goat, right? So in a sense, right, you kind of eliminate, right, a wrong choice. Now, to make it tricky, right, the question is the question is, the host allows you, right, an option to switch door, right? Of course, right, in the scenario we give, you don't know that behind this is a car, right? Behind this is a goat. You only know that this door has been eliminated, right? For example, right? Then the question is, do you want to switch your choice or not? Is it beneficial? Okay. And of course, right, there's a line of argument that says, well, right, after you do that, it reduces down to 1/2, so it doesn't matter, right? It's doesn't matter if you switch or not, right? The chance will be the same. All right. So again, I'm just saying this to give you the sense that this problem, at least, is not that trivial, right? It's not. But right, the true answer is yes, you should switch. If you switch, your chance of winning will be 2/3, and if you don't switch, the chance of winning is 1/3. Okay. But to prove this rigorously, right, this will invoke the law of total probability. Okay. So now let's pause here and see if, right, you can see how you can use the law of total probability to establish what I just said. So, right, you want to look at probability of winning, right? If switch, let's say. Right. Notice the law of total probability allows you to break this into cases, right? To condition it on some extra information to help you calculate this probability. That's the power of the law of total probability. All right. What should we condition on here to make this calculation easy? Any suggestion? All right. What you should condition on is clearly your initial choice. Let's say, right, if switch, condition on initial choice is good, times probability that, right, good, plus probability winning, right, if switch, condition on initial choice is bad, times probability that is bad. Is that okay? That's a law of total probability. Clearly, right, where your initial choices will affect, right, you're probably winning if switch. So let's see, right? course, right? Initial choice, the probability initial choice is good is 1/3, right? Sorry. So this is 1/3, right? But if your initial choice is good and you switch, then probability of winning is 0, right? Because you switch to the bad choice, correct? But if your initial choice is bad, then if you switch, you guarantee a win. So therefore, right, the answer is 2/3. You can do the same analysis to get the probability of winning if not switched to be 1/3. Exactly the same argument. But the point, right, as far as we're concerned here, this is a simple application of the law of total probability. You condition on how your initial choice is. Okay? Any question on this? Okay, so let's give you the quiz. Well, all right, let's try this one. All right, okay. So we will continue at 7.5, okay?
Professor?
Yeah.
If I already did the homework that contained this problem, can I just upload my homework?
Yeah, that's fine,
Oh,
as long as it's correct. If
okay.
it's not, then remember this is graded based on precision, okay? Is there any question before we continue? All right. So just want to say a few things about Friday, right, for the exam. So basically what will happen is so the exam, right, is 80 minutes plus 10, right, for submission. So for your submission, right, again, you don't have to be on responders. You can close responders, all right, but you only have 10 minutes to submit, okay? The assignment will be timed exactly for that. Basically, the one for submission, right, will have 10 minutes extra beyond, right, the other one, right, for the responders. And also, of course, right, the time you submit will be looked at, right, compare with the time that you turn off responders to make sure, right? And also, this is also the whole like kind of show your work, right, to check that nothing extra is added to the submission. But basically, this will happen at the end of the class. So basically, right, so the last part, so let's say, right, our class runs from 6 to 8, right, 6 to 7:55. So basically then, 7:45 to 7:55 would supposedly, right, for submission. And then you subtract 80 minutes, right, from that. So 6:25, right, the exam will start and you will have until 7:45, right, for the exam. And so from 6 to 6:25, basically, well, nothing will happen, right? Well, something, but so I will still be on the lecture Zoom, but no lecture, no new material. Basically, you can think of it as a Q&A, right? You can ask questions about the materials or something along that line, right? Any kind of things you want to be clarified last minute, right? Before the exam. But strong caution here, right? I mean, this is not meant to be a session for like fire rescue, like the responder is not working, what can I do, right? What can I do for you, that kind of thing. No, not really. In fact, right, I cannot do much for you on the responder's side, okay? That's not within my control. I have not like figure out responders from the student side, right? I just assign responders. So the only thing I can tell you is, right, you must have responders up and working, right, and lockdown browser, right? I think these are the same thing, but to take the exam. All right. If you don't, well, long story short, you can't take the exam. Okay. And let's just say that will be unpleasant, right, for both of us. So last minute here, make sure your equipments are working, especially if you're, not in this country, you're in certain part of the world where, internet might be blocked and things like that. I think responders may not interact nicely, okay, with blocking, internet blocking and whatnot. So take extra care, right, to make sure your responder is working. That's the whole point of the equipment check assignment. All right. Any question about this?
Will we kind of just have to write down the answers to the questions like on paper and take pictures of it or something?
Absolutely. Yeah, yeah. That's it. Just like
Okay.
the quizzes maybe, but you cannot use the iPad if you have been using them.
Oh,
That's all.
okay. All right, that was my
Yeah.
question. Thank you.
Yeah, and remember to box your answer, okay? Because you're usually the box is provided for you on the paper on the exam, but here you need to box your own answer, your final answer. That's part of the rubrics, right? Okay. Anything else? Okay. Uh, okay. So let us. Hold on. Sorry. continue with the lecture. So having discussed the law of total probability, right? The law of total probability is so important that it also has a conditional version. Okay. Well, so what is this conditional version? This conditional version, right, is basically about everything conditioned on F, right? Everything is conditioned on F. F is like your universe there, right? And why is this important? As you'll see, right, there will be a problem in the next problem set. Okay, we'll be looking at that exactly invokes this law. So again, right, it's really about, right, you invoke extra information, right? You want to break things into cases, right, to help you calculate the probability. But the only thing is that now the probability in question of what you're trying to compute is a conditional probability rather than a probability, right? You are dealing with a conditional probability. But you want to introduce extra information, all right, in the form of G into your calculation. Then this allows you to do so, right? So again, the point is that, right, G can come in as the extra information that helps you to look at the conditioning. We have to pay back, right? But when you pay back as a conditional version based on F. All right. Any question about this? Okay. So in fact, right, this is actually so important that maybe let us do this. So in case you forget, right, let's do a problem right away, even though it would be a bit more challenging, right, to demonstrate that. Okay, so let's look at this. Okay, so let's take a look at part A first, and then we'll look at part B. All right. So first of all, right, let's make sure we understand the context of this problem, right? This, I'm not so sure. This looks like a basketball final series, right? Or is it baseball? I don't know. But right, you play 7 games, right? But whoever wins the first 4 games, whoever wins 4 games first, right, wins the series. Okay. And so here, right, we have this situation that one team leads 3-0, right? But then, right, for part A, question is, right, find the probability that is A that leads. So this is probably A leads, right, 3-0, given, right, one team leads 3-0, right? That's the question. And so, right, this clearly will be, by definition, A leads 3-0, one team, right, leads 3-0 over P, one team leads 3-0, correct? Okay. Now, of course, right, the top, right, just reduced down to A leads, right? So that would be P cubed. The bottom is, right, either A leads 3-0 or B leads 3-0, right? There's no intersection because, right, there's nothing common here, right? So that would be PQ plus 1 minus PQ. All right. Any question about that? Okay. So, right, A, even though might be not easy, right, whatever, is still straightforward. The focus of the question is on part B. All right, so take a look at B, right? And then the first thing we want to address, right, is why is question B difficult? Or, right, how is it not the same as part A, for example? All right, so who can tell me why B is difficult in terms of calculating the probability? Or maybe I'm wrong here. Maybe it's easy, right? If it's easy, do tell so, right? If you think it's easy, what's the answer? So probability, right? Given that one team leads 3-0, right? Probably that team wins, right? The series. Right? What's the difficulty here? Or not? Either way, right? However you want to look at it.
Maybe because it can be either team, like we can't assign like just like team A or I guess team B just for to like give it a name.
That's correct, right? Exactly, right? So the point here is that, right, the wording, even though, let's say, right, in English, it sort of, right, makes sense-ish as a question, right? Because, right, conversationally, we probably will say stuff like this. But when you really want to sit down and calculate this, right, then you sort of run into a confusion, right? Because, okay, what are we referring to, right? A or B, right? Because, right, notice that one team leads 3-0 actually is not that hard to interpret, correct? Because one team leads 3-0 means A or B, right? Leads 3-0, right? That's fine, we can do that. But the team that wins, right? Clearly, only one team can win, right? Not an or. This is not an or situation, correct? And of course, right? It sort of depends on who we refer to, right? From that to begin with, things like that, right? Okay, so that's why this question is, let's say, difficult. But again, it makes sense, right? It does make sense to ask. It's just the task here is to unravel, right, this information and see what we can do to make the calculation doable, right? And again, right, just to point out, right, this is exactly why things like the law of total probability conditional version, right, is relevant, because we are calculating a conditional probability here, right? And by itself is ambiguous, so it's hard to resolve, right? Again, think of the winning if switch, right? Probability in the multi-hole problem. You need to add extra information to clarify the calculation, right? And the law of total probability will tell you how to do so, right? In this version. Okay. So what extra information do we want to put in? So let's write that down, right? P of E given F is P of E given F G times PG given F plus PE given F G complement times P of G complement given F, right? It's clear what E and F are here, right? What do we want G to be? What do we want G to be?
To me, which team wins in the end? Like A wins in the end?
It's no, no, incorrect, right? Because if you condition on A win in the end, then of course probably A wins the series is 1, right? That too much conditioning. Okay, because remember G is the extra information. Yeah.
So it should be like just one match.
Not one match. Again, right? The information is one team leads 3-0. Where is the ambiguity, right? You want the information just to resolve that
Like
ambiguity.
it might be like 4-0 or 4-1, 4-2, 4-3. Yeah.
No.
Or cases.
Nope. No, right? Again, conditioning is a technique, right? But you want to just condition on the right information. Conditioning on the wrong information will just make you more confused, right? So no, right? None of that. What's the straightforward one that we would need to resolve this? To resolve which team leads to 0, isn't it? And then we say A leads, isn't it? So if we throw this extra information in, doesn't that clarify the whole thing? And we're talking about A here, right? So we will multiply back with P of A leads. I'll drop the 3-0, okay? Does that make sense? So G here, right? What we need is who leads 3-0 here, A or B. That's what we need. All right. And then same thing, right? Probability that team wins series. But now one team lead. Oh, sorry. I say series in my series response. One team leads, B leads, times probable B leads, condition on one team leads. Does that make sense? So this is the law of total probability conditional version. But what we need, right, or the information we need to clarify this structure exactly is who leads 3-0. And we put that in, and paid back by the conditional probability. Are we okay? Any question about this? Okay, so let's see, right? Now you see this part right here is the answer in part A, right? So there's something like P cubed, right, over P cubed plus 1 minus P cubed, right? That's this part. All right. Now for this, you can now safely replace the word that team by A, right? And you can even ignore this, or you can erase this. So I'm being economical, okay? I'm reusing this expression, but in solution, you should write a next line, right? And change it like this, right? Basically, you change this to this probability, right? Why? Because the information that A leads to 0 allow you to rewrite all the other information in terms of A. Does that make sense? Okay, so, right, you know what? Actually, right, I think it's better for me to kind of give you a full version, right? So let's start from scratch. So P, right, that team win series given, right, one team leads, right? So wins here, right, is win series, right? Lead here is lead 3-0, right? So this will be, right, probability that team leads, sorry, that team wins, given one team leads. We add the extra information that A leads, multiply probability A leads, right? Condition on one team leads, okay? Plus probability that team wins, given that one team leads, but now, right, it's B that leads, times probability that B leads, given one team leads, okay? Again, this is the law of total probability, but conditional version. Okay, which is P of E given F is P of E given FG times P of G, G given F plus P of E given FG complement, right, times P of G complement given F, right? And now we know what these are, right, from the previous calculation. So for example, it's P cubed over P cubed plus 1 minus P cubed, right? Now, what I was saying, right, is that this one right here, because you have the information that A leads, so that will resolve into something like A wins given A leads, right? Because you have that information, right, that A is there. So you can replace the team with A. And same thing, right? The second one would be probability B wins given that B leads times 1 minus P cubed over P cubed plus 1 minus P cubed. Is that okay? All right. So now the last thing to do now is to calculate this probability, right? And let's throw in 3-0 here, right? Just to clarify now. And then we'll be done. So what would this be, for example? Given A leads 3-0, right? What's the probability A wins the series? What would that be?
P to the fourth?
Nope. Wrong.
Oh,
P to the fourth, right, is what? P to the fourth is probably A wins all 4 games remaining, right?
yeah.
But we know what? We know that A already led 3-0. Is that true that A has to win all four games in the remaining to win the series?
No, yeah. B could also win, but I don't know how to incorporate that like ambiguity.
No, just think of the logic, right? Very simple. A has already won 3-0, right? Because that's conditioned. And so in plain English, what must A do in the last 4 games to win the series?
Wait, yeah, it has to win 4 times.
No. Yeah. So just to be clear, right? The game is set up so that whoever wins a total of 4 games first is the winner, correct?
Oh,
So
okay.
what you're saying is something like A wins all 7 games. I
Yeah,
think
yeah.
that's something like an overkill, right?
Yeah, I
That's
thought they had to win all 7 games or something. I don't know what I was
no,
thinking.
no. Right, no. Right. They have to win 4 games. Okay, so what would that be then? It will be correct. That's it. Why? Because, right, well, the condition is since A already won 3-0, won 3 games, right? A must win at least 1 game in the remaining 4, right, to win the series. Correct? And of course, right, the only time that doesn't happen is if B wins the remaining 4 games. So the complement of that, right, is the probability A wins at least 1 game in the last 4. Is that okay?
Yeah.
And then of course, right, so this times that, and then by same logic, this times that. Any question about this problem? Okay, right. So again, this is not an easy problem, right? But I want to talk about it first because it, right, is the problem that demonstrate, right, the conditional, right, probability. Sorry, the law of total probability, right, conditional version, right? Okay. All right. Now let's move on to talk about, right, I guess a big topic in here, but you probably will see this. Yeah, no, we use it often, but when we use it, we just kind of use it. We don't even remember the Bayes formula. But so again, this is very popular these days with the whole area of Bayesian statistics and whatnot, right? But at the heart of it, the idea of Bayes formula, right, is about here, right? Switching, you can roughly think of it as switching, right, the order of conditioning. Okay, meaning that let's say so of course I present it this way, but you can think of it as like if you want to switch the order of conditioning, right? So notice that everything here is about conditionally, right? Conditionally. All right. But then you want to switch the order of conditioning. And so, well, First of all, right, let's just chase the formula, right? By definition is this, and then this is the multiplication principle, right? But then notice this is exactly the law of total probability, right? So the law of total probability is at the heart, right, of Bayes' formula. Okay, that's why it's kind of important in many ways. All right, but the formula looks scary, right, in the abstract. There are times when you have to use this formula exactly, right? But usually, if you have to use the formula, then you just kind of reduce it out from the definition like this, okay? And what do I want to say here? That's why you want to kind of memorize, right, the law of total probability, okay, to write down correctly. But for now, right, let us kind of explain the motivation, right, on why you want to kind of reverse the order of conditioning. And just to kind of say that, right, it's actually rather natural to do so, right? So you want to reverse the order of conditioning, right? And the easiest example, for example, right, is medical testing, right? So the reason is as follows, right? Basically, when you test, right, well, without any other better thing in mind, right, think of like COVID as an example, right? When you take a COVID test, right, it's really not a probability that you test positive or negative, right? That's not an unconditional probability when you think about when you take a COVID test, right? The result comes out, right? Fine, but it's not an unconditional probability. It really should be, right? Naturally, it's about a conditional probability. Something like that, right? If you have COVID, right, the test will come out positive. And if you don't have COVID, let's say, right? And why do we put both of these here? The reason, of course, right, is about error, right? You know, no test is perfect, right? No test would completely, right, tells you that you have COVID if you have COVID and things like that. Of course, right, hopefully that the precision is high, right? Meaning, for example, that hopefully this is 99% or something like that, right? And then hopefully this is like low, right, 0.01 or something like that, 1%, right? But point is, right, it's not 100%, right, or not 0.01, right? Okay, things like that. So medical testing, right, is a conditional probability, at least naturally, right? Given that you have the condition, the test will come out this way and that with some precision, right, or with some error. So, but of course, right, the question you ask, right, the question you are interested in, of course, is not this kind of question. The question you're interested in, right, is that you don't have access to this information, right? That's why you do the test, right? And you have access to actually this information, right? You have access to the test result, right? You take the test and, okay, oops, I test positive. What's the probability I have COVID, right? Given that I test positive. All right, things like that. So again, this is not the only time, right? That the only example where you want to switch conditioning, the order of conditioning, right? But this is probably a natural example, right? To show you or to demonstrate to you, right, that switching the order of conditioning actually happens more often, right? And symbolically, it looks very forced. Why do we want to switch E and F, things like that? Because E and F here looks symmetric. But when you put them, right, as a sequence, right, as in like, you know, okay, whether you have COVID or not, right? So this is a tree, right? And then you test positive and negative, right? So that's usually the sequence, right? You traverse the tree in that way, right? And let's say this is 99%, 1%, let's say 5%, right? I'm making up numbers here, right? 95%, let's say like that. And let's say the chance of having COVID 60%, right? This is 40%. Again, right? I'm just making up numbers. I'm not trying to say that people having 60% chance of getting COVID these days, but right, something like that. So you traverse the tree that way, right? Naturally, in terms of, you know, let's say, right, designing the test. But from the user point of view, right, they traverse the tree backward, right? they say they test positive, right? They want to know what's the chance that they come from the COVID branch rather than the non-COVID branch, things like that, right? So here, for example, right, in terms of the numbers I'm putting on, right, the probability of COVID given positive, right, would be the relative ratio of this branch over the sum of the two branch, right? The two branches that have positive. So it's 0.6 times 0.99 divided by 0.6 times 0.99 plus 0.4 times 0.05. Does that make sense? Any question about this? All right. So what else? Right. So basically, right, just like anything, right, the Bayes rule can be generalized to more than two, right? More than two scenarios, right? So here, basically, you have like n scenarios, okay? You have n scenarios, and you have, right, let's say, right, how whatever you're looking at, given each of this scenario, each of this case, from 1 to n, then you can reverse, right, the order of conditioning, okay? But then, of course, right, what you need to know is, right, the probability of all the scenarios under question, right? Things like that. Again, right, you can cook up an example here, right? But let's not go into that. All right, I have an extra slide for some reason, but that's it for the lecture. Any question here? Okay, so let's continue to look at the problems. Okay, so let's go back to the beginning. All right, so you know what? This one is more difficult. Let's wait for that. All right, let's take a look at number 2 first. Okay, so right, this is a long question to read, all right, but to summarize it up, right, the whatever scenario that's given here, right, if you notice, you pay attention to the word, right, that's if, right, if, 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 right, so basically describe things conditionally, or one way, right, as I kind of alluded to before, conditioning. And of course, right, with the status of this problem too, it's natural to represent it in stages, right? And of course, anything in stages, again, tree is a good way to visualize things in stages. Do you have to do tree? No, you don't have to. But tree, right, would be helpful in simple problems. So actually the reverse question is, right, are trees always helpful? The answer is also no, not necessarily, right? There are some problems where, like, maybe basically the scenarios are too many, then, right, symbolic controls there is better, right? So it's just a tool, right? Use it appropriately. But here, right, we're okay. So because, for example, right, we have the first exam, right? So the first exam, where what happens? the probability she passed the first exam is 0.9, right? So pass, not pass, right? And what else? If she passed that exam, she will take the second exam, right? So the tree, right, continues, right, with the pass, right, node on the first one, and the probability she, if she passed the first exam, then conditional probability she passed the second one is 0.8. So here, right, this is the second one, right, is 0.8, right, if she pass, right, and that's 0.2 if she doesn't pass, right. Notice, right, this tree here is like a, what you call it, like a cutoff tree, right? That node doesn't move on, right? Of course, if she doesn't pass the first exam, that's the end of the story, right? And then, of course, the next one will be third exam, right? Where she would pass with probability 0.7, right? Notice again, right? This is a conditional probability, and then 0.3, correct? So, right. Again, right, this tree is not strictly necessary, but it is helpful, right? For a small problem like this to visualize, because we can answer the question easily, right? For example, right, that the answer to A would be what? Point 0.9 times 0.8 times 0.7, right? Is that clear? All right. So now what's the answer to part B? So here, right, that given she didn't pass all three, right? So that information tells you that what branches are you on? Well, you're on any of these branch, right? But not the last one, I guess, right? So on any of these branch, right, the probability you are on the second one, right? So the answer would be something like 0.9 times 0.2, right? Over, right, the sum of this plus that, right? But if you notice, right, actually that's the complement of exactly that. So you can do 1 minus 0.9 times 0.8 times 0.7, right? As a shortcut. But if you want, you can just add this plus that plus that. Okay. Any question? Okay. So let us end, right, with this one. All right. So this one would be one of those more challenging problems, but well, let's kind of, right, finish it here. So the first thing to do, right, is to note that you have to understand, right, the structure of problem clearly, right, before you do it. So here, right, the structure of the problem is, right, A and B plays a series of games until one has 2 more points than the others. So for example, right, something like this. Right, and then let's say, right, something like that, right? So this, right, is an example, right, where A, right, wins the game, right? It has 2 points than the other, okay? So part A asks, right, what's the probability that the game is played with total of two endpoints? So of course, right, for example here, right, the game is played with 8 points total, right? Or, you know, just like really 8 times, right? 2, 4, 6, 8, right? So n here equals to 4, right? But let's maybe ask the first question is, right, why 2n? Meaning it implies that the game can only be played as an even number of points. Is that true? Can we also have an odd number in here? Can the game be played an odd number of times? Can the game end in 3 points? Is that possible? Well, the answer is no, right? Because if you look at the first 2 games, either it's like this, in which case that either A or B has already won, and so the game, right, only lasts for 2 points. What are the remaining cases? The remaining cases is either AB or BA, right? In which case they tie, right? And so if you throw in one more point, right, whichever way, right, whatever, then that just means that one of them lead by 1 point. So the game cannot end yet, right? So it must continue. Does that make sense? So the game, right, cannot be played for an odd number of points. Okay, and so it has a lot to do with this requirement that one has 2 more points than the other to win. That's why. Or if you look more closely, right, then this says that the game actually can be viewed as a block of 2, right? A round of 2, right? First round, second round, third round, things like that. Each round has 2 games, two, whatever, right? And basically, right, either they tie or they will win that round. One of them will win that round and they win the game. Okay. And once you recognize the structure, then the problem will be easy to answer. But anyway, right, I guess we're right on time. So let's revisit, right, this problem next Monday. Okay.
I have a quick question.
Mhm.
So, for the announcement regarding like the check for the material and everything,
Yeah.
it says you have to show your workspace for 1 to 2 minutes, right? And then it also says 80 minutes for like attempting the old midterm properly. So for the check, do we have to spend those like around 80 minutes for that, or is it just 1 to 2 minutes of showing?
the announcement says you have to show your workspace for 1 or 2 minutes. I think that's respondents really, right? I did not say that. What happens is really that, right? You have to show your workspace for the entire duration. Your work table for the entire duration of your exam. Okay. So what
Okay.
happens is usually they have an environment check if that's what you're referring to, right? It's not on my announcement. I don't think so. But once you do the environment check and your facial recognition, whatever, then you can move your camera right away from your face. I have turned off the alarm, whatever, facial detection. And all we have to see is your workspace to make sure that nothing comes in and out. Is that okay? That's for
Oh,
the actual exam.
okay.
Now, the reason why I say the 80 minutes on my announcement is to simulate the exam, meaning that's optional to you. You wanted that 2 extra point of credit, spend 80 minutes. If you think that's whatever, right? You don't care for that 2 points. Yeah, spend some time, right? Check the equipment, go off. I'll give you 2 points for checking the equipment. Is that okay? So I just want to reward people for really simulating the exam. But of course, I do recognize that the 2 points is not worth the effort if you don't want to spend that time. So it's up to you. Does that make sense? But
Oh,
yeah,
that
but
makes
on the actual exam, that's the whole point. You have to show your workspace, and that's why I kind of put it there to encourage people to kind of simulate that out. But that's up to you.
Oh, I see. Thank you so much.
Sure.
Professor, so I would not need like if I finish the like the practice exam in like less than 80 minutes, I it's not like a hard requirement for the extra 2 points, right?
So it's really about spending a substantial number of amount of time, right, to finish the exam, to simulate the exam. So that's why I say it's subjective. This is my extra credit. I can do whatever I want with it, right? But
That's fair.
the same thing is with the actual exam. You're not required to stay the whole duration of 80 minutes to maybe the exam's too easy for you, right? You take 15 minutes, right? In which case you can finish early. But let's say that no one can finish in 5 minutes, right? That would be impossible. Does that make sense? So it's not a hard requirement, but there is some kind of reasonable time to see that you did spend the time on the exam. And that's why there is a submission, right, page to match up your work on that, right? So basically it's meant to simulate the whole real exam. You don't have to spend the whole 80 minutes, but I guess, right, fair guess, you have to spend some time, right, to do the exam. Is that
Okay.
right?
Yeah, understood. All right, thank you.
Mhm. Sure. All right. So, all right. So see you on Friday. If not, see you on Monday. Okay.
Okay, bye-bye.
Yeah. See you.
Professor,
Yeah.
sorry, can I ask one last question real quick?
Sure.
So my environment is gonna be different. Like I just did the environment check. I'm not gonna do the extra credit for like doing the whole 80-minute like practice exam. But
Yep.
is that like an issue since it's gonna be a different environment than the one in the video?
You mean your actual exam is different from the trial run? Is that what you're saying, or what? I'm not sure
Yeah,
I
like
understand.
yeah,
You
I
do.
did the submission. I like recorded my environment, but I'm like in a hotel right now. I'm not gonna be here when I
Oh, no.
actually.
Listen, right? The environment is for the duration of the exam. So as long as your environment doesn't change during the exam, of course you can take exam at a different. I'm not going to hold you to the trial run. The trial run is
Okay.
only meant for you to make sure your equipment functions properly, right? Or better yet, if you're at a hotel and somehow the internet doesn't work in the actual exam, that's really bad. Does that make sense?
Yeah, I'm gonna
But
be at a
I'm
library, so it'll work
okay.
during the
But so
exam.
whatever, that's on you, right? If you switch your environment, you want to make sure that your new environment works for the equipment. But I'm not going to force you to stay with the equipment, the environment of the equipment check. That's not that. Does that make sense? It's really just for you
Okay.
to make sure your equipment works. Yeah.
Yeah. Okay. Sounds good.
Okay. Sure.
All right. Thank you. Have a good one.
Sure. You too.